Y siempre he querido esperar.
Perfecto. No se lleva bien con poco. Que no se vean en persona. Vamos a lo tomar, a ver si llega la otra chica. Sí. Ya te lo compraste, yo consiste aquí. Algo así es que te acostumbraste a ver.
Sí, yo le ponía.
Yo te gradúo ahora, a ver si te ofrecen el puesto de cónsul. El único que estaba considerando.
All right, everyone. Good morning. We're going to get started. So what we're going to do today is discuss a bit about cancer in the context of treatments that currently exist, but focusing on, obviously, the theme of the course, metals. And so we're going to start historically, the most important metal in the anti-cancer field being platinum. So let's try to define what cancer really is, because when people refer to the treatment of cancer, there's a bit of an oversimplification of what the disease is. There's actually a complexity of different diseases, and depending on where it's originating from, there could be a different mechanism of how they actually initiate it. So when we classify it, there's actually a large complexity of diseases, and it's characterized by a heterogeneous variant cells that are multiplying within healthy tissues in the body, and have the capability of spreading beyond the tissue origin, and that is what is known as metastasis. So putting into context in terms of statistics, cancer ranks as a leading cause of global death. There's the burden of cancer incidence, about 19.3 million new cases in 2020, mortality at 10 million deaths in 2020, continuing to rise. And there is a concern because of the COVID pandemic that we might actually reach a possible cancer pandemic as a consequence of limited contact for treatment and so associated things that patients not being able to get their diagnosis and so forth. So when we think about what currently exists for the treatment of cancer, so I often refer to this, those traditional approaches, surgery, radiation, chemotherapies, those still are the most prevalent forms of treatment of cancer. So I put gold in these sort of quotes because they're not optimal, but it's what's more accessible to patients. And so that's why I put it in this context here. So when we're talking about specifically chemotherapy, here we're referring to a type of treatment where chemicals are being used. And so in this context, we're looking at small molecules that have this capability of potentially killing rapidly replicating cells in the body. And so this is one of the most prevalent methods of treating cancer. And you have the platinum family of drugs that are one of the most prevalent forms of treatment. So platinum compounds, cisplatin, and the derivatives being one of the lead drugs that are used for different types of cancer. So ideally, you would want these drugs to be able to, at a certain dosage, maximize activity for killing malignant cells while minimizing damage to healthy tissues, right? That's ideal. But in practice, they are heavily toxic for a number of reasons associated with their off-target effects, right? So they don't necessarily specifically target, these aberrant cells, and that lack of specificity leads to a series of complexities and potentially other diseases. And then you also have, for certain compounds, an acquired cell resistance. And that's actually quite true for the platinum drugs. All right, so the traditional approaches to the production of anti-cancer drugs focus on a screening of different families of compounds. So you see this often when you come across the literature as far as presentation of different families of compounds and trying to assess what activities they have. So you see this sort of broad screening of bioactivity, whether it's anti-cancer, antibacterial, and so forth. And so that will fall in line with more of the traditional approach to trying to discover something that has a potential therapeutic application in this context against cancer. So this is more in the realm of what would be classified as a trial and error approach, or more of an empirical approach. So if you want to classify this more formally, it's more of a phenotypic drug discovery, where you're assessing general properties and you come across a bioactivity that might lend itself to a therapeutic application. So you do see what was termed as a formalized structure-activity relationship. So you try to assess, looking at different derivatives and understanding what about these compounds are lending themselves to more activity, whether it's increased intake into cells, whether it's able to reach a certain target. But the idea is not necessarily that you have a target in mind, right? But the landscape for drug development, particularly in the anti-cancer field, has dramatically changed. So as this was in between 2010 2016, 210 new molecular entities, these are abbreviated as NMEs, they were approved by the FDA. And this was done primarily with NIH funding. So National Institutes of Health pumped in money to try to, develop a number of treatments. And so this is not just for cancer, this is more in general. And so this money helped to lead to these NMEs. And so what you see is that the work that led to the discovery of these particular entities were focused on biological targets. All right, so you identify a druggable target, and so you design your compounds to be able to hit that target. So not necessarily focusing on just testing a series of compounds and seeing, what type of activity they have, but rather looking at a target, seeing what about the target we can try to design something to be able to more effectively hit it. So this will be fall into the category of the target-based discovery. So when we're thinking about this, right, I put into a context the work that Dr. Weinberg does. He is one of the cancer biologists. And so one of the things that he really promotes is this idea of a landmark anti-cancer drug treatment that basically can target the molecular mechanisms that keep cancer cells alive, right? So how do you go about doing that? It's obviously not something that's very easy to do. But what I want to talk a bit about is what are some of the things that you can consider that are features of cancer or different types of cancer to try to be able to design something that can be more targeted. So I sent you a couple of articles that the title is Hallmarks of Cancer. I didn't actually send you the original article. I sent you the subsequent articles. And so the mission of these articles is really to try to identify these commonalities, these features that people can try to think about when they're designing an anti-cancer agent. So in this article, this was in 2011, the Hallmarks of Cancer, the Next Generation, they assign 8 distinctive and complementary hallmarks of cancer. So these are capabilities acquired during the multi-step development of human tumors that enable growth and metastatic dissemination. So growth, right, these cells being able to replicate, but also being able to spread beyond their origin. So let's talk a little bit about this. So you have what is sustained proliferative signaling. So trying to enable them to be able to proliferate, which means to be able to replicate it and be able to be more aggressive. Also to evade growth suppressors. So there are a number of proteins that the function of them is to be able to signal cell death. Well, these a number of cancer cells have the capability of going around the machinery to suppress these suppressors. And then you have also resistant different types of cell deaths. You have enabling replicative immortality, inducing angiogenesis, and that's basically the formation of new blood vessels, and that leads into the next one, which is then activating invasion and metastasis. So that's the spreading from the site of origin. Reprogramming cellular metabolism, so trying to, surviving in an aberrant environment, using different biomolecules to be able to do so, and also avoiding immune destruction. As you probably are familiar with immune therapy being designed for attacking cancer cells, and so there are mechanisms in place to try to avoid that. And so additional features that have been highlighted are the following, and that is enabling processes. So that being the genome instability and also tumor promoting inflammation. So this is highlighted in the article. These are essentially the hallmarks of cancer incorporating these enabling processes. But in 2022, so last year, this next version of identification of hallmarks of cancer highlights what the author feels is an emerging hallmark or an emerging enabling characteristic. And so these being unlocking phenotypic plasticity, non-mutational epigenetic reprogramming, polymorphic microbiomes, and synaptic cells. So these being key features that can potentially enable the aggressive nature of cancer cells. All right, so basically what this is boiling down to is those features that can provide, some sort of guidance into these cells being capable of replicating. So we briefly talked about the microbiome and how it can help us to, as we survive with a pretty extensive and personalized microbiome. Well, apparently there's some indicators that by having the microbiome, let's say, becoming aberrant itself, can lead to potential origins or enabling of conditions that can allow cancer to prosper. You have senescent cells that are basically cells that have lost the capability of replicating, but they are quite capable of resisting death. And so that's a feature of cancer cells or tumors that that is hard to drug against. And so you also have these different capabilities that allow for these cancer cells to be more able to evade drugs that have been designed and allow them to be much more capable of surviving. So here then is the incorporation of these additional features as part of the hallmarks of cancer. So there are additional things I want to point out, and we will look at them throughout the course. And that is that it's well documented that there is an enhanced permeability and retention effect. And this is, I should have put the abbreviation, it's known as the EPR effect. And so essentially what that means is that you have a leaky vasculature, and that leaky vasculature allows for things to be able to become in closer contact with cancer cells. And so people try to take advantage of that as it allows for a possible better targeting of cancer cells. So in addition to having that leaky vasculature, you have what is known as a lack of an effective lymphatic drainage. So what that means is that you can have things that can get closer into cancer cells, but because you have the lack of that drainage, there's a larger retention of them. So a big space where people are trying to design is the nanofield by making nanoparticles that can be retained in this area and providing for a bigger drug load and delivery. So we're going to talk about that later in the course, but I wanted to bring that up because that is an important feature of surrounding, let's say, solid tumors. And then you also have a number of features that are what I call metal-based hallmarks. So those characteristics where there are a number of essential metals that, just as they're important for our regular cells to be able to thrive, they also are important for cancer cells to be able to replicate. So I've shown you this figure before, but I'm now going to put it into the context of those features that are, stand out because of this dependence of cancer cells for iron. So what we're looking at here, and I talked about this before, is when you compare a healthy cell to a cancer cell, what you have is this loss of this homeostatic control of how much iron is getting in, how much iron is getting released. Because cancer cells thrive with iron. And in fact, iron is extremely important for allowing for cancer cells to be able to replicate much more aggressively. So there's an important protein or enzyme in this context ribonucleotide reductase, which is an iron-dependent protein, okay, and it requires iron to bind in order to become activated. And so that protein is responsible for DNA synthesis and consequently for proliferation. And so you see a lot of these features where there is less, less ferroporins, so less release of iron, less storage of iron, because there's a much more utility of that metal in order to enable these cells to thrive. And another big feature is the prevalence of the transferrin receptor. And that makes sense because there is this, higher prevalence of iron getting in, so you need more receptors to be able to bring in the iron-bound transfer. All right, so I want to highlight this key thing about the complexity of solid tumors, in that solid tumors are not composed of one type of cancer cell. So that's where oftentimes you get this sort of misconception when people report results that are, anti-cancer related, and they report it against single cell lines. That's an oversimplification of how, reactive something may be. Because a true tumor, a solid tumor, it consists of a very heterogeneous composition of different cells. So here's just a cartoon representation of this, where you have these cancer stem cells that can be transformed into different types of cells that are listed here. So you have like those immune inflammatory cells, you have invasive cancer cells that, as the name implies, have the capability of potentially being engaged in metastasis. So you have this complexity of cells, in addition to those that can benefit from the growth of vasculature to be able to move from site of origin to other locations. So another representation of this is here, where you have this solid tumor, and then you have this, this flow of blood in the vicinity, and how that can lead to this sort of complexity of the chemical or the biochemical environment of the cell. So anything that's close to that vessel would have a normal amount of, or normal levels of oxygen, but the further away that you are from the blood supply, the less oxygen you have. So then you have cells that are hypoxic. So under those conditions, then they will thrive differently than those cells that are more close to the actual, blood supply. So then you have to think about, well, something that, let's say, photodynamic therapy that depends on oxygen, maybe it's effective for something close to blood supply, not so much for things that are, in a more hypoxic environment. So these are things that are important to think about when you're designing something and how effective it can actually be. All right, so I bring up this slide, and it's actually looking at the older form of the hallmarks of cancer. But I bring it up because I'm just highlighting here what are different approaches that people have been developing in order to target each of these different hallmarks. And so I'm actually not going to focus on any of these, but I just wanted to draw your attention that there are efforts made towards targeting the different hallmarks of cancer, and in line with this target focus drug design or drug discovery. All right. Yeah, go ahead.
Yeah. So in a patient, is there a way to identify which of those different types of cells is predominant?
So I think there are efforts to do like more patient-specific things. So it would depend on what type of cancer it is, right? So my understanding is that depending on the cancer, you can isolate cells and try to see if you can design something more patient-specific, but that's obviously going to be limited, right? Not everyone's going to have, let's say, the insurance to be able to do something like that. But yeah, I don't know too detailed about how that would actually work, but there are ways to understand what type of, what is, what is more prevalent in a given tumor. So what I'm going to show you here is going from the basics of what people do in order to identify just some of these pharmacological properties, and then going to a little bit of discussion about the use of animal models. So here's just a representation of how people go about characterizing just the property of a compound to exhibit a cytotoxic effect. So that terminology, cytotoxic, basically implies the ability to be toxic towards cells. So it doesn't necessarily mean that you have the capability of killing cells. So you can possibly have the capability of being anti-proliferative. What that means is that you are stalling the capability of proliferating. But that doesn't imply that it's actually causing cell death. So within the cytotoxicity realm, there are different things that you need to gauge in order to determine what effect a particular compound has. And so an example like this, where people have designed a cell culturing assays, here, it can be a little bit of an oversimplification, but it's a beginning approach to just get a general understanding of a potential therapeutic application of a drug. So here we have an example of taking mammalian cells that have the capability of growing in vitro. And so normally, not all cell lines have this capability, but you have the capability of commercially available cells that you can, what is called passage. And what that means is that you can put them into a plate and you can grow them across different cycles and be able to study them. So the typical approach for growing mammalian cells would be such as this, 37 degrees in a humidified atmosphere, possibly having some amount of carbon dioxide. The purpose of the carbon dioxide is to be able to have an equilibrium with carbonate so you can control the pH environment in which these cells are growing. But very important, cells are a living thing. So they need to have sustenance. You need to provide them with nutrients for them to survive. And so here's just a representation of a type of media. There are different media that have been formulated for the purposes of culturing cells. And so the idea is that you want to replicate, let's say, the composition of blood. Come as close to it as possible so that you are favoring the conditions that will allow for cells to be able to grow. And so here are some of the components of these media, where you have some of the more conventional salts that are important at high concentration. You have some of the common acids, vitamins, very importantly, glucose is a source of energy, glutathione, very important redox agent. We come across glutathione quite a bit. You also have the supplementation of serum. So the typical type of serum that people use is fetal bovine serum. And so that's supplemented. The reason why that's supplemented is because it doesn't survive very long. So you can buy the media that's quite long lasting, where you supplement it with the serum. And so essentially there, where you're supplementing it with proteins that are important in order for the cells to survive. In addition, depending on the type of experiments that you're doing, you might also want to supplement with antibiotics so that you don't contaminate these cells. And as you can see, this particular media is red. Often you would have media that has a dye. And the purpose of the dye is as an indicator. So you all are familiar with that to tell you that you're at the right pH. So cells are very pH sensitive, and that indicator is put there for that purpose of knowing that you are in the conditions in which you're growing the cells are at the right pH. Very important is then thinking about if you're going to study a compound and you're treating cells with this compound, is how you're going to deliver the actual compound. And so you would think, okay, I'm just going to solubilize it. But even then, not every compound is soluble. And so I'm bringing this up because in the context of metals, this is actually really important to be conscious of, is the choice of solvent is not always compatible with the type of compounds that you're working with. And so it's quite common to see people use solvents like DMSO, DMF. These are considered more universal solvents when water doesn't work, but and they are miscible with water. So that's why people like to use them. But oftentimes, DMSO can actually degrade compounds, either by serving as a ligand itself and then making a compound transform into something that is not actually active. Also, these type of solvents, as you can imagine, at a high enough of a concentration, they are going to be cytotoxic. And so you get, I've come across a lot of literature where I see really high percentages of DMSO being used, and it's not very clear to me if what they're reporting are the consequence of the compounds in the setting or the consequence of the DMSO itself being cytotoxic. So from my own personal experience, this is not something I'm referencing, something from personal experience. Anytime you use greater than 2% volume by volume of DMSO, you're going to induce cytotoxicity into your cell lines. And so this article I'm highlighting because it specifically says never to use DMSO for cisplatin, carboplatin, or other platinum compounds because it actually causes for those compounds to become something different and often something that is not going to be active. So it's very important to be conscious of when you deal with metal compounds. The solvents that you're using, does it actually transform your compound? This is on top of what I've discussed early in the course, is the aqueous speciation that your compounds may actually dissociate to some extent. So this is an added layer to think about, how a co-solvent that can be used to solubilize something may actually be not helpful when you're trying to gauge activity. All right, so when we're thinking about then trying to test the activity of a compound versus cell lines, what are some of the common ways that people do it? And one of the most common approaches is by doing a simple a cell plate assay. So here I'm just showing you a very standard 96 well plate. The idea is that you use this to do a number of experiments where each of these wells is a place where you can put your cells, and then you can do different treatments of them. And so that's pretty common today as a first level approach to try to gauge the effect of a compound at different concentrations. So what you normally would do would be a dose response experiment. And so depending on the type of cells, there are going to be those cells that have the capability of being adherent. And what that means is that they have the capability of growing onto the plate, and they will grow at the base of the plate. So these types of plates are designed for that purpose of cells actually adhering onto them. And then you're able to do your work with those types of cells. Now, there are cells that are non-adherent. And what that means is that they are suspended. They just remain in suspension. So you obviously have to be very careful, because now you don't have the luxury of the cells being on the plate. You have to be careful that you end the pipetting process, that you don't actually lose cells along the way. So the standard to do is to incubate the cells into these plates first. And the reason for that is that you want to acclimate. Acclimate is get those cells accustomed into the environment of the plate. So that's important to achieve. Now, it's going to be a little bit different for adherent versus non-adherent cells, how long the acclimation time will take. For adherent cells, the common advice is to do it for a day. For non-adherent cells, it's probably not a day, it's probably more along the lines of maybe an hour or so they can acclimate into in that environment. So for adherent cells, the day is because they have to develop proteins that are going to help them to anchor onto the actual plastic and to be able to become adherent. After that point, then, you want to gauge the activity. And so that can range from anywhere from 1 day to 3 days. And so some people will argue, well, we want to see activity within 1 day because that would just tell us how effective it is in very little time. But the reality is that a lot of these biochemical mechanisms take more than a day to become activated. So it's preferred to do a longer time frame of gauging activity just to be able to assess the overall cytotoxic potential of a compound. But you will see people looking at 1 day, 2 days, and 3 days. But it's always recommended to do more than just a 1 day time point. And so a common approach to be able to gauge whether or not a compound is cytotoxic is to use a dye. And so oftentimes a dye is a way of or at least a relative quantification of the number of living cells, or the appropriate word would be viable cells, that are present under a given condition. So in the treatment with these compounds, or just in the treatment with the media that you're using. So the National Cancer Institute recommends that you measure the number of cells after the equilibration point. So after the cells have become acclimated, so that's like your starting point of how many cells you have. And then you determine how many cells you have at the end point, whether it's 1 day, 2 days, or 3 days. All right, so one example, there are different ways that you can do this, but just giving you one example is to do this, this approach, which is the MTT assay. So this is the compound that is used. So essentially what this compound is going to measure is the viability of the cell. So if you have a cell that's live, viable, what is going to happen is that that compound will react with a mitochondrial reductase, and you'll get this formazine that forms, and that what you'll see is a change of color. The change of color is the formation of a purple color, which you can observe at an absorbance of 595 nanometers. So the color, the absorbance, is going to be proportional to the relative number of viable cells. So this can be MTT, or you can use derivative MTS. So same thing, the end product is going to be a formazine that you can monitor at 595 nanometers. And so the idea is that you're going to gauge those viable cells. And so I say this is a quantitative approach because it does follow Beard's law. So the more intensity you have, the more it correlates to the viable cells. So you'll see something like this. So if you're doing a sort of a dose response, you get a sense of where there are viable cells with concentration, you're starting to not see viability. Okay, so what you do then, you collect that data, you process it, and you produce this type of plot where you're looking at the cell viability, and I meant to write percent cell viability. Okay, you look at percent cell viability, and it's percent relative to control, the control being the media that you use to grow your cells. and you're looking at the different dosages or the different concentrations of a compound that you've treated. So what you're going to see, and this is, I plotted this in a log scale, so that you can see this type of curve. And this type of curve is sort of the ideal curve where you get at low concentrations, no response at all. You get 100% cell viable cell, meaning that there has been no effect on the cells. Then at a higher concentration, you see that the viability starts to decrease until you plateau, and in an ideal experiment, you reach 0 viable cells. At 0 viable cells, you basically have no living cell at all. So what you're trying to gauge is the relative activity of the compound. So there are different parameters that people try to report as far as the activity, or how potent is how active the compound is at affecting the viability of cells. So an important parameter that you see often reported in the literature is the IC50 value. So that is the inhibitory concentration at which 50% of the maximum number of cells are viable. So you will often get people misinterpreting this data. So you'll say like, oh, as you reach this concentration, as an example, you see that 50% of the cells are dead, but that's inaccurate. What this is reporting is the number of viable cells. It's not measuring any dead cells. And it only tells you how you're affecting the proliferation of the cells. So this type of assay is an anti-proliferative assay. So you gauge how much the viability has been affected. You can get some indication of cell death. So obviously, if you reach 0 viability, you've actually have killed cells. But this is one of those experiments that people classically misinterpret. So the normal number to report is an IC50, but in reality, IC50 values, people are not so careful on what they report. So often what you will see is an IC50 value that for data like this, where you don't actually reach 0, but they will report to you at what concentration you reached 50% of the total signal, okay? And that's not a true IC50. That is relative to that particular experiment. So just be a little careful there as to what numbers are they reporting? Are they reporting a true IC50, as in 50% of the maximal signal, or are they reporting a relative number? They won't necessarily say. You have to actually look at the data and be able to tell what you're actually looking at. Okay, so I mentioned to you the National Cancer Institute, so the NCI, they suggest measuring the number of viable cells at the equilibration point. So if the number of cells for day 1, so day 1 being at the point before treatment with the actual compounds. So you measure that number, and then you try to compare with what the number is at the end of treatment. So with that information, you can actually get more information about the effect of the compounds if they even have the capability of killing cells. So here, with this type of information, by knowing the day 1 number of cells you had compared to what you have at the end, you can determine what is referred to as the LC50. And the LC50 is the lethality concentration at which 50% of the day 1 cell numbers has been decreased. So if you go below how many cells you have initially, that implies that the cells have been killed. Go ahead, Karen. So it's going to be relative. So let's imagine you incubate your cells, adherent cells for a day, you do the MTT, you record that intensity. And then you do your treatment, say you probably need a different plate. You do your treatment after the 3 days, you record the intensity. You compare that intensity to the intensity at day 1. And then that's how you measure it.
The index separation will last.
Most people don't measure it the first day.
Oh.
They just go into the final point and they compare it to control.
Okay.
Yeah, exactly. Yeah, but most people don't do the first day just because it's more time intensive and then you end up using more material. So they typically will skip that. So what is a desirable IC50 value? So here that gets a little bit tricky because sometimes people will, depend on the number heavily as far as activity, but it's a combination of having a desirable IC50 value and what is known as a therapeutic index. Okay, so I'm going to define that in a moment. So for practical purpose, ideally, we would want IC50 values to be less than micromolar. But you will come across a lot of compounds that are interesting that do display IC50 values that are in the micromolar range. But the reason why you want to go lower than that, if possible, is that you have to think about how that would translate to potential administration to people. Because to get something at micromolar concentrations, you have to think about how much you would have to administer to effectively get that, and especially depending on the route of delivery. So let's say you're going to do something that's an intravenous delivery of a compound. How are you going to get an effective concentration that reaches that level? That's something you have to think about. So here I just give an example of a calculation based on like the average amount of human blood in the system, how much concentration you would have to have initially that when you deliver into the body, you reach an effective concentration that's micromolar. Obviously, this is an oversimplification because most treatments are not a one-time treatment. There are over time. But you have to think about what dosage you need to reach in order to even potentially get at a level that would be therapeutic, right? So that's why you see a large, push for IC50 values that are very low micromolar or in the nanomolar range. It's for this practical purpose. But that's not the only parameter you really need to think about. You also have to think about this idea of a therapeutic index, right? So what does that even mean? So that means how effective is this compound against a cancer cell line or cancer cells in general versus a non-cancer control or series of controls? Because what you want to see is that this activity is actually you're going to compare IC50 values against a non-cancer cell line versus IC50 value against a cancer cell line. And you want to see that the IC50 for the non-cancer cell line is much, much higher, right? Because then you have what is known as selectivity. So that is what is meant by the therapeutic index. You want this ratio to be extremely greater than 1, and that shows you that there is selectivity for cancer cells. But even this, you'll see this in the literature, and it's a bit exaggerated, where people will use, let's say, only one non-cancer cell line to test against a series of different cancer cells and say, well, against this non-cancer cell line, we have selectivity. But again, that's a bit of a misleading, because you should probably gauge a series of different non-cancer cells in order to have some sort of indicator of a therapeutic index. Another important thing about IC50 values, and being a little cautious about how you think about this in terms of general activity. So here's just an example of a ruthenium compound. So the key point is not to be so exclusive of IC50 values on just one type of cell line. So this particular ruthenium, or these ruthenium compounds, they are active, but they are active against secondary metastasis tumors, not the primary tumor. So that's an interesting property that you wouldn't have identified if you only focus on cell lines that stem from the primary tumor. Under those conditions, these compounds would have really poor IC50 or really high IC50 values, and would have been just thrown out in terms of the possibility of their activity. But screening against the secondary metastasis cells show that these are actually quite potent against those forms of the cells. So very important thing is that you need to screen against different cell lines of a tissue to get some sort of picture of how effective a compound is against a type of cancer. Okay, so don't just use one cell line and say, this compound is really good against breast cancer, because it's actually not going to be enough information. And obviously, this point about you want to have compounds that are as targeted as possible. Right. Another really important thing when you're gauging activity is to try to correlate activity to, let's say, the mechanism of action of the drug and how much of that drug is effectively getting inside the actual cellular environment. So here I'm just going to point out ways that you can measure this. When you're looking at something as metal compounds, you can just simply measure the metal itself within the cellular environment and see how much actually got inside the cell. And that gives you an indicator of just the general uptake of the drug. So these are just tools that you can use. You probably have all come across as an analytical chemistry, atomic absorption, spectroscopy. Some of you probably have done some ICP, some form of ICP, maybe ICP-MS. And so these are the general things that you want to measure. The moles of the metal versus if you can count the number of cells, or sometimes you don't count cells, you count like another indicator like the number of proteins. Whatever you can do to get a gauge of how much compound is getting inside. Those type of approaches that are more elemental based can be a little bit cumbersome, as they are quite intensive in terms of preparation of sample. So where possible, and this is not always possible for all types of metals, if you have an imaging agent that can be used for imaging a particular metal, we've talked about this for iron. There's some imaging agents that are used for measuring labile iron. Well, that can give you a way of quantifying how much compound is actually getting inside. And so you have people that have made what are known as ratiometric probes. These are probes that will give you a relative amount of how much metal is actually within the cell, because it gives you a signal specific for the probe bound to the metal and a signal for the probe when it doesn't have metal, right? So there's a way of giving you some quantitative information. But in addition to this is trying to profile what is known as uptake plots. And so uptake plots is measuring uptake over time. It can be an indicator of the type of route by which your compound is getting in. So maybe some compounds may be permeable. Maybe some compounds, as we've talked about earlier in the course, they may be small, but they're charged, they don't have the capability to come in, so they may need some sort of transporter. And so you get some information about using these types of plots to determine what potential route of entry is a compound experiencing. And maybe you want to target a particular transporter to enable your compound to get in. But I will make this disclaimer here, that increased compound uptake does not always equal to greater potency, because there may be a case where a compound needs to target the outside of the cellular environment to be effective. So that's something that you want to just be a little cautious that don't put too much into how much compound gets in, but certainly that parameter is going to be very helpful. All right. So I've already mentioned a bit about limitations of cell work. You don't want to just have one cell line as an indicator of a type of cancer, but what other things that is an oversimplification? So what I've described to you thus far are types of cell works that are what are called two-dimensional, meaning that you're looking at one cell line, and if it's adherent, you're looking at a layer of it and how the compound is affecting that layer of cells. So when you're working with commercially available cancer cell lines, those have been engineered to be more prevalent or more capable of surviving the conditions in which you're growing them. So they're not necessarily the best at giving you an indicator about the general bioactivity of a compound. That's why oftentimes you see people switching to work with primary cells. So, taking actual cells from patients and working with them to try to test activity. But that's not something that's easy to come around, right? Not everyone has access to patients. You need to have protocols approved to be able to do that. So something like this, where you're working with something commercial, is a beginning step, but be conscious of what these limitations are. So people have been moving more into the direction of three-dimensional cell culture. So what does that mean? So essentially, you're trying to mimic how a solid tumor. Remember, not all cancers grow in this format, but this is just a way that if you're trying to look at a solid tumor, I've already mentioned to you that this is grown in a very heterogeneous manner. While growing them three-dimensionally at least gives you that perspective of how treating them with cancer cells might be able to be effective. And so you have just this idea of what is referred to as a tumor spheroid, so this three-dimensional structure, where you get a sense of the microtumor environment. So here's just an example where you have this spheroid, and then depending on where you are in terms of the, from the extracellular phase of this, from this outside portion of the cell, you're going to get this sort of difference in the biochemical environment. Here, the example is that in the region that's more at the center, you're further away from, access to oxygen, so you're going to have more of a hypoxic environment. That's why here it's labeled as necrosis, because that region, those cells are probably dying from lack of oxygen. So this kind of gives you more of a perspective of a more realistic way in which cells would grow, but still, three-dimensional cell culture has its limitations because you're still working with one type of cell line, but you're putting it into a matrix that allows it to grow in a three-dimensional fashion. All right. So cell work, even though limited, still gives you some indicators that you can work with to profile whether a compound is worth moving on to what would be the next step, which would be work with animal models. And so here's just examples of types of models that exist. These are more general that I'm going to refer to. So you have those that are called the patient-derived tumor xenografts. So these are tumors that are taken from human cancer patients and they're implanted into, obviously, a non-human host. So typically would be mice. And so what you would do is you would grow several generations in the different host mice. And so, for instance, live cancer patient cells, in addition to tumor genomic data, can be given to investigators to perform what I was mentioning to Javier earlier, patient-specific drug studies. Okay. The thing about the limitations about this type of animal model is that you're going to do this work under what is called immune compromised conditions. And why am I saying that? It's because you're putting something that is foreign to a mice. And so you're going to have to, in order for them to grow, do some amount of suppression of the immune. So you're not going to get the effect of the animal's immune system against that, the tumor and against whatever treatment you're looking at. So you lose out on that information. Then you have what are known as genetic models. And this is where a tumor implant derived from the same animal. So a mouse tumor is implanted into a mouse to be able to gauge the growth of the tumor and how a compound responds to it. So in this context, then you actually are able to take advantage of the immune and how that responds to treatment. But of course, the limitation here is that you have something that is not human derived. So you're going to have that associated limitation. All right. So with all that said, so this gives us a perspective of how you go about doing some just general screening of compounds and what makes you decide on moving on to an animal model. So what I want to focus our attention now is to platinum, because platinum is still a lead metal in the anti-cancer field. There are many drug treatment regimens that incorporate platinum as a lead drug or as something that is part of the general treatment. All right, so let's look at this small molecule. And so we know platinum-2 is a D8 in terms of its electronic configuration. And so because of that D8 electronic configuration, it is a square planar compound. All right, so this particular compound, in terms of its activity, was discovered serendipitously. And so this was in an experiment where I think I mentioned this to you in the first day of lecture, where they were working with the growth of bacterial cells, and they were working with platinum electrodes, and they noticed that the bacteria were, it looked like they were dying. And they wanted to understand what about the experimental conditions was causing for this bacterial death. And what they discovered was that the electrodes were reacting chemically and forming into cisplatin. And so the cisplatin was attacking those bacterial cells, and that made the scientists wonder if it can attack bacterial cells, does it have the capability of doing the same thing with mammalian cells? And so that's where it led to the discovery of cisplatin having that anti-cancer effect. So we say that, but cisplatin is something that can attack all cells. That is the reality of this compound. So you will see it is considered the gold standard in as a metal-based drug. In many papers, when they report activity, they like to report it with respect to cisplatin across different types of cells. So what I want to do is briefly incorporate some fundamentals. So I'm going to get back a little bit into fundamentals to put in perspective some of the features about cisplatin. So here, what I want to focus on is this idea of compound lability. And I've referred to lability a few times when we talked about the labile ion pools in cells. It's the idea of being reactive. But when we're looking in the context of ligand exchange, lability is a measure of the rate of a metal being able to exchange its ligands. And so here we have this simple reaction where we have a ligand that I've labeled X, which would be our leaving group. And then we have another ligand, which is labeled Y, which would be our entering group. So we're basically doing, in this context, a nucleophilic substitution. And so at the end, we still have a compound, probably with the same coordination number at the end, where you basically have substituted the leaving group X with the entering group Y. And so lability, or how reactive the ligand exchange is going to be, is measured in this parameter. If the ligand exchange occurs with a half-life, less than or equal to 1 minute, that's classified then that the compound is kinetically labile. It will react rapidly for exchanging ligand. If that number is greater than 1 minute, then the compound is considered kinetically inert. So inert doesn't mean that it doesn't react, it just reacts slowly. Okay, so that's just in the field of inorganic chemistry, how you go about classifying lability. And so how was this property measured for metals in general? And so a classical experiment that was done was this one, where basically you're measuring the rate of water exchange. So we know water can serve as a ligand for metals, and so that's what was the experiment that was done. You have a compound with aqua ligands bound to it, and they use isotopically labeled water, and you were looking at that exchange. Isotopically labeled water coordinates the metal being released into the solvent. And so from there, you're able to quantify your rate of water exchange, okay? And from here, your rate expression, right, you're able to measure this parameter K, which is in this case, the rate constant as a measure of the lability. Excuse me. So here is a way that we can profile different metals in terms of their general ligand exchange lability. So you can see this in a general inorganic chemistry textbook. So Alex, you'll probably see this towards the end of your course. So what we're looking at here is the relative water exchange as a measure of the lability of different metal ions. And so what we're seeing here, depending on how you want to look at this, you can look at this in terms of the lifetime. You can look at it in terms of the rate constant of the water exchange. So what we see is a division here, where in this range of the plot, you're looking at those metals that are kinetically inert. So they are slow to ligand exchange. Then to the right, you have those metals that are kinetically labile. They are rapid for ligand exchange. And so if you look here, we see platinum falls into the category of something that is kinetically inert to ligand exchange. I'm not going to go into the details of why that is, just to report that that metal typically doesn't exchange ligands very quickly. All right. There is one factor that can actually increase the rate of ligand exchange, and this is known as the trans effect. Okay, so here I'm just representing the trans effect in this fashion. So we have the square planar platinum, and so what the trans effect implies is that you have a ligand that's in a position trans to a ligand that's going to leave. Okay, so I have my trans ligand and I have the leaving group, okay, the leaving ligand. And so there's something about the property, the chemical properties of the trans ligand that will induce the lability of the leaving group. And so here I have this trans effect series where from left to right, they have an increasing capability of inducing the release or the lability of that leaving group. All right, so here's just an example where, for instance, if you start off with this compound here, you have platinum with the four amine ligands coordinated to them. And so you want to generate this compound at the end. So what we're looking at is what happens when you start to add ligands. So here in this context, we're looking at chloride. So we have a first chloro group coming in. That chloro group, it can replace any one of those amines. It doesn't actually matter because they're the same ligand. So arbitrarily, I put the chloro group right here, but I could have put it in any one of those four positions. But now the question is, you have a second chloro group. So we already see the answer, right? We see where it went. But why is it going there? So it's going there because when you look at the trans effect series, we look up what ligands are there. We have a chloro group, okay? And we have an amine ligand here. The chloro group being to the right can induce more labelization of something trans to it. So we have a chloro group trans to the amine group. That's going to be more effective at inducing the release of that amine group than the amine to itself. And so that's why the second chloro group lands in that position there. Okay, so that's how you go about looking at what the trans effect is and how it affects it. I'm not going to the details as to what specifically about the ligands is inducing this. That's something that in the inorganic chemistry course, you can go into more depth. All right. But when it comes to cisplatin, it's actually not the lability that's the governing thing about the activity of this ligand, okay? Here, it has to do more with stability, okay? So stability, when we talked about that early in the course, we talked about affinity. How tight are these ligands bound to the metal center? Well, it turns out that the chloro group, its affinity to the platinum is lower than the affinity of the amine to the platinum. So if you're thinking about delivery of cisplatin, and as it's going from the extracellular environment into the intercellular environment, so the cytoplasm, what you're going to see is an effective concentration of chloride being decreased. So within blood, you have chloride at a concentration of 100 millimolar. But then within the intracellular environment, cytoplasm, you have chloride at a concentration at 4 millimolar. Okay, so that is a significant drop, right? Factor 25. And then what we see then is that is a low enough of a drop of concentration such that one of the chloride groups will become dissociated. And so it dissociates and that gets replaced by an aqua ligand. So we start to see the beginnings of how platinum becomes reactive, because I already mentioned to you, platinum is inert to ligand exchange. But in this context, it's the relative stability of how tight the chloral group is. And when you decrease the effective concentration of the chloral, now you've liberated this binding site. And now you can start to think about, well, now the platinum has this capability of binding to possible biomolecules within the cellular environment. So here's some representations of the aqueous speciation of cisplan. So here we have cisplan represented here. We introduce it into an aqueous environment. Obviously, aqueous environment, you've decreased the amount, or there's no chloral group available. So you can have one aqua ligand or possibly even a second aqua ligand coordinated to the platinum. What we're seeing here is that in addition to the aqua ligand coordinated to platinum, we get hydrolysis, so a loss of a proton from the water molecule. So on the right, we see more equation of the metal center as a consequence of the affinity of the chloride groups to the platinum. Right? So that's a possibility for the aqueous speciation of the platinum. But now, go ahead.
It's not clear to me why water enters the second
Oh, because you're lowering. So if you're thinking about the affinity constant, right? Let's just imagine. Well, let's say platinum is obviously not the way it's going to be, but let's say 2 amine ligands plus 2 chloral ligands, and you get your equilibrium, right? Right, and you form your beta val expression, right? So you're going to have your product. So depending on what the actual beta value is, and then if you have a decrease in the chloride concentration, you're lowering the effective, how tightly that's going to be held. So you have to just think about the relative concentrations there. So you can see the dependence like that. So depending on what this number is, and then how that's going to get affected by, the amount of, you drop the amount of chloride groups is going to favor the dissociation of the chloride. Here, I'm giving you an oversimplification because we're not looking at necessarily that. We're looking at this as being our product that forms. So there's only one chloride group, but you can start to think about like how tightly bound the chloride groups are. And then if you drop the concentration of the chloride group or the chloride in this case, then that's going to weaken the affinity of that and results in dissociation. Okay. So to make this picture even more complex, so the previous slide looked at the compound in water, and you're looking at the aqua ligands replacing the chloride groups and possible hydrolysis occurring. Okay, but let's imagine we add in something else. Let's imagine we have carbonate. Carbonate is common in blood. We've seen carbonate for serum transferrin, right? How it helps to coordinate iron. Well, carbonate has the capability of coordinating to platinum. So that can make it even more complex because now you can have chloride groups getting replaced by the carbonate. And so what effectively is happening? You start off with something that is neutral, then you get something that is dianionic, and that could potentially affect the effective amount of that compound going inside the cellular environment. Because something neutral might be permeable, something dianic most likely is not. And so you can imagine how that could affect how much the metal is getting inside. All right, I'm bringing that up because this is sort of, as we've talked about before, the reality of thinking about the effective concentration of how much something can get inside the cell environment. And so when you're looking at cisplan as a drug that gets dosed, this is a typical amount of dosage of the compound. And so some of the pharmacokinetic or pharmacodynamics of this particular drug, it has a half-life for a rapid phase of platinum clearance in plasma after infusion of about half an hour, okay? And then most of the platinum that you administer through infusion is actually eliminated in the urine, okay? So you can imagine an effective concentration is starting to drop a lot just by how quickly it's cleared from the body. And then of that amount, you're gonna have about 65 to basically all of it the metal being bound to blood plasma proteins, one of the main proteins being albumin. So I gave you a picture of cisplatin going into the cellular environment, but most likely it's not cisplatin. It might be something like this, where you have the platinum coordinated to albumin with at least one of the chloride groups removed. And one of the common amino acids that's proposed to bind to platinum is the histidine or the methionine. Histidine being something more intermediate in terms of its hard softness, and methionine being something that's more in the soft range. Here is a representation of platinum from cisplatin coordinating to different sites within albumin. And this, I bring this protein up because I've said this before, it can affect a number of drugs in terms of their capacity to enter into cells. In this context, you can see how it can bind to different parts of the protein, and what has been proposed to be its binding sites being, these amino acids, histidine and methionine. So it's believed that a good portion of that cisplatin that actually reaches into the blood environment becomes protein bound. And as a consequence of that, here's one potential source of toxicity, where it binds in sites where zinc it may actually be bound in the protein. It's believed that albumin can help to transport zinc. It may not be the primary transporter of zinc, but by replacing the zinc, you can see how that can have sort of a systemic toxicity. All right, but pretending that we have intact cisplatin being able to go into the cell environment, so that compound can potentially enter into the cell environment, and then because of the decrease in chloride, you get the transformation into this monoequated compound. But there's also evidence to show that it can be transporter assisted. And so it's believed that it can use the copper transporter protein, CRT1, in order to enter into the cell environment. So it has two different routes by which it can actually enter. But then you have to think about this, which is the efflux of the compound. So obviously cisplatin is not endogenous, so it's not a natural part of the body. But the body has the capability of recognizing something foreign. So in the context of cells, it can try to remove the compound. And so here is where you find a source of cellular resistance or acquired cellular resistance. So these are two proteins. They're ATP7A, ATP7B. These are referred to as multi-drug resistance proteins. Both of them are copper trafficking transmembrane proteins, and they are known to be involved in the efflux of cisplatin. So the cell becomes resistant, recognizes this compound, and it basically stimulates their release from the cellular environment. So what is observed is that those cells that become resistant will have a higher expression of these exporters, and so much less effect of the cisplatin itself. Another corollary sort of system for affecting the relative activity of the cisplatin or leading to acquired resistance is glutathione itself. So the glutathione is this trimer, so it is a peptide, but it consists of these three amino acids. And so a really important function of the glutathione is that it helps to regulate redox within the cellular environment. But as a consequence of this thiol group here, it has metal binding capability, and other features of the peptide also favors metal binding. But that thiol group is actually really important because that can bind to platinum being a softer metal, and so you can transform cisplatin into something that is platinum coordinated to glutathione, and then in that form, then the compound becomes inactive, and then it can actually become efflux from cells using the multi-drug resistant protein MRP2. All right, so this is another way in which the platinum can be biotransformed in a way in which the cells becomes able to protect themselves. All right, but it's believed that the primary target of cisplatin is DNA. So that's always where you see people talking about platinum. They talk about how effective is the platinum at targeting DNA. And so the reality is that most likely DNA is not the true primary target, but an effective amount of it can, result in cell death. And so what we see is of the amount of cisplatin that is administered, 1 to 2% can actually reach the nucleus and be able to form adducts with the DNA. So here's just some representation of adducts that the platinum can form with DNA. So one of the more cited ones are these, the cross-links. So you have cross-links where the platinum coordinates to the N7 site of the base guanine. So you have coordination to two guanines, either in an intrastrand form or an interstrand form. All right, so that's one of the more commonly cited ways in which platinum can bind to the DNA, and it can lead to breakage of the actual DNA. But you also have some of these other ways in which platinum can coordinate to the DNA, where you can have what are essentially monofunctional adducts. So it coordinates to simply one of the bases, not to two bases. Or you might have these sort of ternary complexes where you have the platinum coordinated to the DNA and possibly coordinated to a protein, something like that, right? So these are different ways in which that platinum can interact with the DNA and lead to structural changes that can affect the replication of the DNA, but also can lead to the breakage of the strands. So this is just another representation of the platinum being able to do this, coordinate to the guanines of the DNA. All right. So how can the structural distortion really affect the overall properties of the DNA? So it's just a representation here, where you look at the platinum coordinated, right? But then how that basically starts to disturb some of the hydrogen-hydrogen bonding interactions that stabilize the DNA structure. That can distort the molecule, and that can lead to eventual sort of the breakage of the actual molecule itself. So here's a sort of a classical approach to try to gauge that using a simple agarose gel. So an agarose gel is used to run nucleic acids, something like DNA. And so here is just a representation of the effect of platinum at different dosages and what type of effects are actually observed. All right, so here what we're looking at in lane one is just two different forms of DNA. One that's linear DNA and one that's compact DNA. So in an agarose gel, a compact DNA will actually run through it further along than something that's linear. Okay, so that's what we're seeing in the first lane. Form one being the compact form, form two being the linear form. So what we're seeing here are the different dosages. So I don't actually have numbers here, but the different dosages of the platinum and what effect it's having. So what we observe is that at a high enough of a concentration, you see that the form one is becoming more like form two. So what does that mean? Well, it's disrupting the structure so that no longer have this compact structure. Now you're going to have something that's more linearized. And so we see that behavior here. But then at higher concentrations, we start to see the formation of these bands. These bands are fragments. So now you start to cleave the DNA, and these smaller fragments can now move further through the agarose gel. So this is basically an indicator of the effect that the platinum can have on the DNA. This is a way that you can determine if a particular platinum compound is actually directly binding to DNA, and if that binding is affecting its structure. So it's a really nice approach to be able to gauge that. All right. So in addition to what I mentioned to you about the ways in which you can grow and acquire resistance to platinum by the overexpression of efflux or the efflux system or these transporters, you also have a resistance that is grown due to the DNA repair system itself becoming, activated more so. And so you have these DNA repair mechanisms that can basically break up the coordination of the platinum to the guanines. So that if you can break that up, then plus the efflux system, you can more effectively withstand the activity of the platinum itself. So this is the nucleotide excision repair, or the NER. All right. So as I mentioned to you, DNA is what people propose as the main target of cisplatin, but the reality is that cisplatin is reactive because of its relative affinity of the ligands to the metal itself. And because of that, it has prevalent interactions with different biomolecules, which is the source of its toxicity. So I already mentioned to you how it can be toxic even before it reaches the cellular environment by possibly displacing zinc from albumin. These are a few other ways in which it could be contributing to its cytotoxicity against cancer, but also could also have some effects that are off target. So these are just a few additional things that are not DNA related And so people have been able to determine these interactions, both targeted and untargeted manner. So what I mean by targeted is that you take a particular molecule, you see if the platinum can bind to it, what effect does it have? Untargeted meaning that, let's say you treat cells with platinum compound, you then you lyse the cells and try to see what proteins may have been affected or what metabolites may have been affected. So targeted versus untargeted have led to the discovery that platinum, as one can expect, has the capability of interacting with RNA. So that makes sense, it's a nucleic acid. And it's been observed with these yeast cells that the platinum can bind more effectively to RNA than it can to DNA. It has the same capabilities of forming these guanine crosslinks. So that's pretty intuitive there. Also, it has the capability of binding to a number of proteins. As an example, is this NHE1 membrane protein, which is a sodium hydrogen exchanger. It's believed to be a possible initial target as it's getting inside the cellular environment. And that can cause a lowering of the intracellular pH, increase membrane fluidity, and can trigger apoptosis. You also have this capability. So in addition to what I mentioned to you about affecting zinc within albumin, you can also have this effect on zinc finger proteins. So zinc finger proteins have this common feature. So you probably have seen this in biochemistry, where you have the zinc coordinated in this tetrahedral fashion to cysteines, histidines, or they can be all histidines or they can be all cysteines. But these are really common features, these zinc finger proteins that contain this type of zinc-bound modality. So what has been observed is a type of transmethylation where the zinc is replaced by platinum, which can be a bad thing, right? So probably within a cancer cell, that's fine, right? But if that actually enters in healthy tissue, it can be quite bad, right? Because these zinc finger proteins, they're responsible for many different activities. So these are just a series of them, just to give us an overview of the importance of these type of structures. You also have evidence to show that cisplatin can also interact with this protein tubulin. So this is a 50 kilodalton protein, self-assembles to form microtubules. These microtubules are involved in cell division when the chromosome is separated during mitosis. So if you interfere with this particular protein, that can affect replication of the cells. Another important enzyme, we'll actually get back to this enzyme when we talk about gold, is thyroredoxin reductase, or the thyroredoxin reductase system. So it's a very important system for regulating disulfide and dithiol in redox. And so what can happen is that the platinum that interacts with glutathione before it even can get expelled from cellular environment, that can actually inhibit glutathione peroxidase 4 or GPX4. So I'm not sure if you remember that, but that protein is a protein that if you start to inhibit it, you can then trigger ferroptosis. So it is observed that cisplatin can actually trigger ferroptosis because of this type of interaction. By interacting with glutathione, which is one of the primary cofactors of GPX4, you can inhibit that protein. And so you have the capability of also inhibiting the thyroredoxin reductase system in a manner that's analogous, because in this type of protein, you have really important thiol or selenium groups in the actual active site that the platinum can coordinate to. And when it coordinates to, it can basically block it from being active. It's believed that this type of interaction, it could be a source of the ototoxicity, that is the loss of hearing. In fact, many people that get treated with cisplatin have a loss of hearing. You also have evidence for cisplatin interacting with stress response proteins. So a lot of evidence for platination of these proteins that are important for regulation of the central metabolic pathway. And there's a lot of evidence for platinum just getting all over the place, where it can hit the mitochondria and it results in uncontrolled ROS generation. It can trigger the lysosome degradation. And if that happens, you have the release of these proteases, which are, can cleave a lot of different proteins. And you can also trigger the endoplasmic reticulum stress, right? So all that to say that, yes, platinum is a lead drug, but it's also quite poisonous. And these are the reasons why it has that effect. All right, before we go, any questions or any doubts? All right. right, everyone. So Monday, I want to have a special session. I'm going to figure out the timeframe. I'll let you know. So, so there are a few things that I have a conflict with, but I'll figure it out and I'll let you know by this evening. Okay. All right, then. Have a good weekend.
Bye.
Bye, all.